Okay, it's starting to record. Okay, so are you able to see the screen?
Yes,
Yes, sir.
Yes, sir. Yes, sir. Yes, sir.
Okay. It's not going into slideshow mode. Okay, so last class we here. Okay, that is how to do the optimization of two variables with the contours. Okay, so you have to draw the contours of the objective function, and it will touch the feasible region at one minimum point. And if you draw further contours, it will touch the feasible region at one maximum point. So you get minimum value of objective function and maximum value of objective function. So with this, we'll try to do some one or two simple engineering problems in two variables. So first is minimum weight optimization of a tubular column. Okay, so you can see a column here. Column is like a pillar, okay, which the axis is in the vertical direction. It is subjected to load P, and it has a length L. So the cross section is defined by the radius or diameter is 2r and thickness of the tube T. So R and T are the design variables. So to do the minimum weight, you have to reduce R and T and thus reduce the cross-sectional area. So what are the constraints? Okay, first is the objective function. Minimize the weight. So weight is equal to 2 pi RT into L into rho. These are a constant. L into rho are constant. That value will be supplied to you. R and T are the variables. Then two constraints are there. First is that compressive stress should be less than the yield stress in compression. So compressive stress is P divided by area. So this is actually the yield stress in compression. Then buckling load of the tube must be more than the applied load P. So this is the equation for the Euler buckling load. That is pi squared EI by 4L squared. So P should be less than pi squared EI by 4L squared. And the value of I for a tubular section is pi by 64 into outer diameter raised to 4 minus inner diameter raised to 4, and the value of I simplifies to pi r cubed T. Okay, so two constraints are there. Okay, compressive stress and buckling load. Now, as I told you, P, L, rho, E, sigma, Y are all constant. So the values are supplied to you. Okay, so we can substitute this numerical value. So we get an expression for objective function, expression for first constraint, expression for second constraint. So you can see that R and T are the optimization variables in all these equations. There is no other variables. Okay, so first let us plot this. Plot this feasible region. Okay. Okay, so you have to plot this region. So what you have to do is that to plot the feasible region of constraint one, assume it is a equality constraint first, and you plot this curve, that is 10 raised to 7 by 2 pi RT minus 2.48 into 10 raised to 8 equal to 0. So you draw this line. Okay, this is the equality constraint line. It is equal to 0. Okay, so this will divide the xy plane into two regions. So this line is equal to 0. One side will be less than 0. Other side will be greater than 0. So which is which? Okay. So what you do, you substitute a value of r and t in this equation. So 10 raised to 7 by 0 minus 2.48 into 10 raised to 8. So this is infinity plus infinity minus 2.48 into 10 raised to 8. Okay, so that is still plus infinity or positive. So this is the positive side or greater than or equal to 0 side, and we want the less than or equal to 0 side. So this is our region. Okay. So all values of r and t in this region are satisfactory to us. Okay. And the variable range is not given, so you can assume this variable range. R is from like 2 centimeters to 10 centimeters, or 0.02 meter to 0.1 meter. Okay. So this is feasible region of first constraint. So next, plot the feasible region of the second constraint. So first you plot the equality constraint or equal to 0. So this is the curve where the second constraint equal to 0. Okay. So one side will be negative, one side will be positive, or one side will be less than 0, other side will be greater than 0. How to know which side is which? So what you do, you take one point here, r equal to 0, t equal to 0, and you substitute it. 10 raised to 7 minus 0. That be equal to 10 raised to 7, that will be positive. So this is the positive side. So automatically the other side becomes negative. So we want this side only. So all values of r and t on this side is acceptable for us. Okay. So now you have to find intersection of the two constraints. So you can plot it. Okay. So this is constraint 1. Okay, this is constraint 2. Constraint 2. So this hatched region satisfies both constraints. Okay. Hatched region satisfies both constraints. That is the intersection of the two constraints. Okay. Next is, let us plot the contours of the objective function. So what is the objective function? It is something into r into t. Okay, so f of rt. Okay, so it is looking like this is a surface. Okay, so r is here, t is here. This is f of rt, the objective function. So straight away you can see that maximum weight is around here. Okay, this is the maximum weight. It is around 9,000 kilogram. Okay, this is the maximum weight. And minimum weight is 0, where r equal to 0 and or t equal to 0. Then cross-sectional area becomes 0. So minimum weight is 0. So you can draw the contours here. This is the contours using the MATLAB command. So this objective function has to be sliced into various heights. Okay, and all these slices are the contours. Okay, so this is done with the MATLAB. I wrote the equation of this objective function, and I gave the contour command, like contour 20, then it will give 20 contours. So you have this plot. So you can see that here is 9,000 kg, and here is something like, this dark blue color, like 1000 kg. So all values of R and T here give 1000 kg. Okay. Something like that. And also looking at this contour, you can see that it is 9000 here and 1000 here. So the objective function is decreasing in this direction. Okay, so now we are superimposing the feasible region on the same contour plane, contour plot. So what you see here is the feasible region. This thing is the feasible region. Okay, feasible region, which is the intersection of constraint 1 and constraint 2. So you can see that which is the smallest contour which just touches the feasible region. So F is equal to 2500 is this contour, or weight of 2500 is this contour, and the weight of I think 1500 is this contour. Okay, 1500 is this contour. Okay. Okay, so so this red point represents the smallest weight of the pillar. Okay, and that weight is approximately this contour, which passes between 2000 and 1500. So this particular contour, maybe 1750 kg, is the smallest contour which just touches this point. Okay. So this 1500 is a lesser weight, but it is out of the feasible region. So the 1750 contour, which is interpolated contour, is the smallest weight which just touches the feasible region. So this is the minimum weight. And the corresponding values of R and T can be read from here, like 0.04 and 0.16. So what is the maximum weight? Maximum weight is somewhere here, 9000 kg, and it is well inside the feasible region. So the beam will not break under the 9000 kg load. Beam will survive now under 9000 kg load. So suppose you are asked to maximize the weight of this beam, then the answer is 9000 kg, and the values of T is 0.01 and the values of R is 0.35. Okay, so this is maximum, this is minimum. Okay. So next we look at our first beam problem in
Sir, I have a question, sir. I'm sorry to ask. Can I ask, sir? Sir, for the given objective function and with the constraint that we are having, if we find the optimum weight of the beam, so corresponding to that weight, what will be the factor of safety? That will be minimum in that way, right, sir? Safe minimum factor of safety.
Yeah, because this includes the yield stress, this is satisfying yield stress center. So this is the factor of safety 1 only, because it depends on what factor of safety is your yield stress.
Okay, sir. Okay.
Suppose you take yield stress as the actual yield stress in the table, then this will be factor of safety 1. Suppose you take your yield stress as already factor of safety with factor of safety 2.
Okay, sir. Got it.
Okay, so that is how.
Thank you, sir.
Okay, so this is our first problem. We started in 2 variables, then we reduced it to single variables. So we ignored the 2 variables. Now we will take up the 2 variables. So in this first problem, we wrote this objective functions. Okay, first the value of objective function is this, value of first constraint is this, value of second constraint is this. Okay, so here the design variables are B and D. Okay, and there's one more constraint. D is less than or equal to 0.1. So let us plot the feasible region. So this is actually D is less than or equal to 0.1. Okay, the last constraint. So this is the first constraint, this is the second constraint, and this hatched region values will satisfy both constraints. Okay. Satisfy both constraints. So now we have to draw the contours of objective function. Contours we have to draw like this. Okay, so this is the contours of objective function. F is equal to 250. That's the maximum weight. 250 kilogram or something is the maximum weight, and the weight decreases. Okay, so yes, your weight is equal to 7 kilogram. This contour's weight is equal to 7 kilogram. And you can see that this feasible region is just touching this. Just touching this 7 kilogram contour. Okay, so this feasible region is just touching this 7 kilogram contour. So weight of 7 kilogram is just attainable if you use a D equal to 0.1 and B equal to 0.01. Okay, 0.01. Okay. So this is the minimum. So what is the maximum weight of the beam? Maximum weight of the beam is 250 kilogram, which satisfies all the constraints. So if you are asked to maximize, then this is the answer. Okay. That is D equal to 0.1, B equal to 0.35. Okay, so this is the maximum. Okay, so this type of problems will be asked for the assignment and first quiz. Okay, but the contours will not require any MATLAB. It will be either simple circular contours or straight line contours. So linear programming problem studied graphically. This is highly important because many people study and talk about linear programming without understanding what it is. So linear programming typically occurs in economics or industrial engineering. So here the objective function and constraints are linear. So why is it linear? It is linear because objective function and constraints are summation of various costs or losses. So that is why it is linear. So we look at the structure of a simple linear programming problem with an example. So a company makes X numbers and Y numbers of two type of products. Okay, so the profit of making first that is X type of product is rupees 150 per item, and the profit of making Y type of item is rupees 175 per item. So the various constraints and objective function which involve manpower, storage, and transportation limitations are written below just as an example. Okay, for example, you want to maximize the profit. So 150 rupees is the profit per X component, 175 rupees is the profit per Y component. So depending on the numbers of X and Y, the maximum profit can be summed up. Then you can see this is mainly a transportation constraint. Okay, just for example, so 7 rupees is the cost of transporting one X component, 11 rupees is the cost of transporting Y component, and the total transport cost for X number of items and Y number of items should not exceed 77 rupees. And here, like 10 rupees is the storage cost of one X item, 8 rupees is storage cost of one Y item. So total storage cost of all X items and Y items should not exceed 80. Then X should be less than or equal to 9, Y should be less than or equal to 6. Maybe some manufacturing constraints. Okay. So let us plot this feasible region. Okay. plot this feasible region. Okay, the first is this x is less than 9. Okay, this is x is less than 9. Then y is less than 6. This is y is less than 6. So that will give this rectangle. So next is 7x plus 11y is less than 77. So that gives this region. Okay. So this side will be 7x plus 11y greater than 77, which we don't want. One more line constraint is there. Okay. 10x plus 8y less than or equal to 80. So this is 10x plus 8y greater than 80, which we don't want. So the intersection of all this feasible region is this red area. This red area is the intersection of all our feasible regions. It is a polygonal region. Okay, so next you have to draw contours of objective function. So up to now we only plotted for feasible region. Next, contours of objective function. This is our objective function. So to draw the contours, you have to give various values of f1, f2, f3, etc. That is various slices of the objective function. This is f1, f2, f3, f4, etc. So you can see that all these contours will be the parallel lines. Like this line is 0 equal to 150x plus 175y. Another line will be 10 equal to this 150x plus 175y. Another line will be 50 equal to 150, equal to same thing. Another line will be 100 equal to. So how to draw this contours? So because it's a linear objective function, we need to draw only two contours first. So we draw this 0 contour and we draw this 10 contour. So we know that all the other contours will be parallel to these two. So this is these two things are not required. Okay. Okay, so we need to draw only two contours because from these values 0 and 10 we know that increasing value, increasing direction of contours we know. Increasing direction. So the next contour equal to 20 can be drawn with a set square with this gap. This gap of 10 will give 20. And then with set square we can draw another parallel line again with a 10 gap. Then this contour is 30. So by drawing successive parallel lines you can draw the successive slices of the objective functions. 60, 70, 80, etc. So to draw the contours of linear objective function, you need only draw two straight lines first, and the remaining can be drawn with set squares or with a ruler. So now we'll go to the final figure. This is the feasible region. I draw, okay, feasible region is here. I draw the contour f of xy equal to 0 and f of xy equal to 0 and then f of xy equal to 10. So now I know that increasing direction of objective function is like this because 0, 10. Okay, so you can see that this contour of 0 just touches bottom of the feasible region. So minimum value of objective function is 0 because it is just touching bottom of the feasible region. And maximum value of the contours can be obtained by drawing successive lines until you hit this red vertex. This red vertex is the farthest point of the feasible region. Okay, so that, and this particular value of the contour is 1417. This is the maximum profit you can get is 1417 rupees without violating the transportation cost and storage cost and all that. Okay, and the corresponding XY values can be read from here. Okay. x is equal to 5, y is equal to 4. So your x star and y star. Okay. Sorry, this is y star. Y star. Okay. So this is how this linear programming problem is done. So you would have started. Okay. So next we look at some special features of this linear programming problem. I think I'll erase these things. Okay. So for linear objective functions, plot two contours. So these things we already studied. Okay, how to draw the parallel contours. Then another important thing is that linear programming problems will give polygonal feasible regions like this. Okay, it will be always a polygon like this. The solution is one of the vertices. It may be here, 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 here or here. Okay, suppose in this problem we slightly change the objective function, then the contours may come like this. Okay, in that case, this will be the solution. Okay, and suppose we change the objective function again, so contours may come like this. Then it will hit here. So sometimes one polygonal. Okay, so solution is one of the vertices. Okay. Then sometimes in some rare cases, one polygonal side may be parallel to the objective function. Then all the points on the side are solutions. So let us see that. Suppose we wipe all these things. Okay, now suppose contours are coming parallel to this side. Okay, it is parallel to this side, then all the points on this side are solutions to the objective function. Okay, that's a very rare case. So when you do the simplex method in linear programming and all, first you start with 0, 0, and then you try various vertices. Then you try this vertex, then you try this vertex, then you try this vertex, and then you try this vertex. So you successively substitute all these vertices in the objective function and find the maximum value. So that is how that simplex method works. Okay, so that is the end of the introductory part of the optimization. So next we look at
Professor, just one query.
Okay.
Am I audible?
Yes.
Sir, you were saying in the exam we'll be given a similar assignment or something wherein we'll have to plot the objective function and as well as the contours, right?
Yes, sir. So
you have any example of such thing wherein
I will
you
give
can
an
tell us
assignment,
how?
but at that time we can work out. Okay, I will give assignment.
Okay,
so
sir. Okay.
That time we can.
We're not familiar with how they are. We're not familiar.
Yeah,
with
when
how to do
you
it
need a
because,
graph paper, you have to plot it in a graph paper. You have to plot the equations of line
Understood.
on graph paper. You can shade the feasible
Okay, sir.
region. Then you can plot the straight lines as contours, parallel lines on the graph.
Okay, Professor. Clear.
Okay, so next topic is some single variable optimization algorithms. First is concept, then is algorithm. We can start little bit here, then we can stop. Okay. Okay, so basically in this lecture we are going to see some algorithm of finding the minima or maxima of single variable problems. Okay, so x only is the variable. So how to find this minimum or maximum? So that is the goal. But first we look at some other concept also. So first is we always talk of global minima, local minima. So for single variable function, how do you define the global minima? So First of all, there is only one variable x, and it is a subset of the set of real numbers. So x can vary from minus infinity to plus infinity. So that is the meaning of x is a subset of real numbers. Then x double star is said to be a global minima if this f of x double star is lesser than any value of fx within the range of minus infinity to plus infinity. So let us take this value of x. So this f of x double star is smaller than this f of x. So let us take another value of x here. So this f of x is more than this f of x star. So whatever value of x you take, that f of x should be more than f of x double star. That means f of x double star is the global minimum. And what is the meaning of local minimum? So as far as optimization is concerned, if you want to define a local minima, you have to specify some range. Okay, so the x star is said to be a local minima if f of x star is the smallest value of f of x within the range of plus or minus epsilon. This is plus epsilon and minus epsilon. So if you want to define a local minimum, first you have to define the range in which it is a local minimum. Okay. So f of x star is a local minima within the range of minus epsilon to x plus x minus epsilon to x plus epsilon if this f of x is the smallest value compared to any other value of f of x within that range. That is the thing. Then some important point for the single variable optimization is, first is the stationary point, that is df by dx equal to 0. So where slope is 0. So that is called stationary point. So at x equal to x star, that is the optima, then df by dx is equal to 0. That will be the stationary point. Then maxima and minimum. So if d squared f by dx squared is negative, then it's a maxima. If it is positive, it is a minimum. Then there's another important point called saddle point, which you may not know. Saddle point is called inflection point. So you can see this is the illustration of saddle point. So x star is called a saddle point if f of x is increasing on one side of this x star and f of x is decreasing on another side of x star, and also the slope is equal to 0. That is df by dx is equal to 0. So under this condition, then you will get a small flat region. This is called a flat region or tabletop region. Okay. So this particular region is called saddle point. So at the saddle point, you can see that the df by dx equal to 0. D squared f by dx squared also will be equal to 0 at x star. So what is the meaning of d squared f by dx squared is equal to 0? So df by dx equal to 0 means slope is 0 here. Okay. D squared f by dx squared equal to 0 means the rate of change of slope is also 0 for some region. So the slope will continue to be 0 for some region at the saddle point. So that is why it's called tabletop region, because it will be the slope is not 0 at one point, but it will be 0 for a small region centered around x star. Okay. So this is the saddle point. The saddle point is important because some of the optimization algorithms will get stuck in the saddle point thinking it is maxima or minimum. Then one example is there for this given objective function. obtain the stationary points. That is where the slope is 0, and study their properties. Study their properties means check if they are maxima, minima, or saddle point. Okay, so let us first find stationary point by equating derivative to 0. So equate first derivative to 0, and if you solve this equation, okay, then you get the real solutions of 0, 1, 2, 3. Okay, so at all these points, slope is equal to 0. Now let us check second derivatives at all these points. So this is the equation for second derivative. Let us check the sign. So at x equal to 0, first derivative is 0 and second derivative is 0. So it is a saddle point. X is equal to 0. X equal to 1, first derivative is 0, second derivative is 60. Because it is 60, that is positive value, it is a minimum. Then the x equal to 2, first derivative is 0, second derivative is minus 120. So because negative value, it is maximum. Then x equal to 3, first derivative is 0 and second derivative is 540, positive. So it is a minimum. This is just an example. So next is something called convexity, which is highly important. So we'll just start this concept and continue in the next class. So convexity is a most important property of optimization problems. So actually, strictly speaking, before you do any optimization problem, you're supposed to check the convexity of the problem. So if it is convex, it means that it will have only one minima within that variable range. Okay, you can know in advance that it will have only one minima within that range. Convexity of optimization problem is highly important. Okay, so convexity of optimization problem can be divided into two parts: convexity of feasible region and convexity of objective function. So two separate convexities are there. And so if both are convex, that is feasible region is convex, objective function is convex, then the problem can have only one minimum. Okay, one local minimum. Okay. Sometimes in rare cases we can get multiple local minima, like in the linear programming problem where two sides are parallel. So this we'll study later. Okay, many local minima. So if it's convex, there will be only one minimum within the variable range of the problem. So first we look at the convexity of the feasible region, that is convexity of a set, then convexity of the objective function. So what is convexity of a set? Okay, so suppose this is the feasible region. Okay, y and x are the two variables. This is the feasible region. This is a set of feasible points. So that is why it's called convexity of a set. So this is the feasible region, and it is a set of feasible points. So it falls in the definition of a set. So we look at convexity of the feasible region. Okay, so convex set or convex feasible regions. The convex set is one where the line joining any 2 points in the set is contained inside the set. So you can see one convex set. This is a circle. So if you draw any line here, it will be exactly contained inside the set. So another convex set is a polygon. Okay, so if you take any 2 points here and draw the straight line between them, it will be contained within the set. But this is not convex. So if I take these 2 points here and draw the line, it is going out of the set. So this is non-convex. So what is the mathematical definition of convexity of a set? So you take any 2 points x1, x2 in the set, and then any linearly interpolated point x must lie inside the set. Suppose I take this polygon. So x1, x2 are the 2 points. I draw the line joining x1, x2, and all these are interpolated points lying between x1 and x2. So all these interpolated points must lie within the convex set. So you can see this is a non-convex, and the definition will fail here. So when I take any two x1 and x2 here, so some of these interpolated points are going outside the set. But of course, if we take x1 and x2 here, all the interpolated points will be inside the set. But the rule says that this should be valid for any two x1 and x2. Okay, not just this, but this also. Okay, so that is the thing. Then, so this is convexity of the visible region. Then another important thing is that intersection of two convex set is also a convex set. So we know that circle is convex, polygon is convex. Okay, so their intersection is also convex. Okay, then many constrained regions or feasible region give convex sets. For example, this constraint equation we saw in one of the worked example. This means that the circle of radius 1 and this less than 0 means all the points is whose radius is less than 1. So this is a convex set. Okay. Then 0 is less than x less than 3. This is also a convex set. Because if we take any 2 points and draw the lines, it will be contained inside the set. Of course, if you take any 2 points on boundary, then all the points will be in boundary, but that is acceptable because boundary points are also considered to be inside the set. So this is a convex set. So their intersection will also give a convex set. Okay, so all these points are a part of the convex set. So suppose you take these 2 points, you draw a line, any interpolated x will be inside this hemisphere. Okay. Okay, I think we can stop here. Next class we'll continue from here. Okay.
Sir, I have a question. I'm sorry.
What is that?
Sir, I have a question.
Okay, you can ask now.
Sir, this is regarding the problem that you have shown regarding the optimization of volume of beam, the weight of the beam. So you had also told that, sir, that if we want to optimize a function for the minima, but if you optimize the same function for minus fx, it will give the maximum, right, sir?
Yeah.
So, sir, in this particular case, we have seen that we have derived the minimum, what I meant to say, value, I think it was t is equal to 0.01 something and t is equal to 0.1.
Where? Which example?
So beam wala, beam section, beam, sir, optimization of beam.
Okay.
So, sir, in a similar way that you have told that the maximum beam can be 9,000, if I remember the value correctly.
Okay.
The maximum weight of the beam can be 9,000.
Yeah, like this one. Okay. Okay.
Sir. So if we go to the next slide, sir, I will tell you. Next slide, sir. I'm sorry. Next slide. This, sir. Exactly. We can come down, sir. We can come down. And one more, sir. Yes, right. So here the D and B value are were to be optimized for the minimum weight of the function. And that came to be around 0.1 and 0.01.
Yeah, okay.
D and B respectively. Now applying the similar concept, sir, if I use the minus fx function to maximize the weight, how it can be justified, sir? Can we
you have to draw the contours for minus of.
Okay, so it will be reverse of this, right, sir?
Okay, then This will be like, okay, -7, huh?
Right, sir.
I don't know how the contours will come if you slice. Okay. So,
Okay.
so this will be -7, this will be -250. Okay, then how the MATLAB will plot the negative contours?
Okay.
Will this come here or will this come here? It depends on that. Huh?
Probably it will go into third quadrant.
Huh?
It will go into third quadrant. Other
So
side.
-7 will become red color then, because that
Okay.
negative value is higher than minus.
But that concept is valid for this problem as well, right?
Yeah, it is valid for this also. Okay.
Fine.
Then I don't know. Then probably contours may come like this.
Exactly. The mirror of this. You're
They
right. sir,
come
right, sir,
from
right,
this side. Probably.
sir. Right,
Huh?
sir. Right, sir. Got it, sir. Got it. Thank you.
Okay. Okay. Stop recording. So tomorrow is the stop.